Hello, physics students. I'm going to talk to you for a little while about velocity time graphs. So on my screen is a velocity time graph. The vertical axis is the velocity in the horizontal dimension. That's what this x symbolizes in meters a second. The horizontal axis is the velocity, is the time in seconds. So the first thing I want to mention is the difference between instantaneous and average. So instantaneous velocity is just the velocity at any moment. So if I pick some points, I can figure out what the instantaneous velocity is. For instance, at t equals 0 seconds, the graph is at 0 meters a second. So the instantaneous velocity is 0. At t equals 4 seconds, the graph is at 10 meters a second. So the instantaneous velocity is 10 meters a second. And then if I go to 10 seconds, t equals 10 seconds, at that moment, the graph shows that the object is moving at -5 meters a second. So at rest is how we'd interpret 0 meters a second, not moving. Positive velocity at 4 seconds, and negative velocity. Remember that if the velocity variable v has an x in it as a subscript, that indicates that this positive velocity is to the right, because that is indicating horizontal velocity, and this negative velocity is to the left. Okay, I'm going to clear my writing. Okay, now let's talk about average velocity. So one simple way to determine the average velocity of an object is v average equals sum of the velocities, say 2, divided by the number of things. This we call the simple average. You learned it in math class. So if I look at the interval from 0 seconds to 4 seconds, then the initial velocity is 0, and the second velocity would be 10 meters a second. And I divide that by 2, I get v average equals 5 meters a second. And that works fine for a constant acceleration. Like this situation, this line with this slope indicates a constant acceleration. However, if we try to do the same calculation, this was, remember, from t equals 0 until t equals 4 seconds. Suppose we try to do the same calculation for t equals 0 up until t equals 8 seconds. I hope you can see this is not going to work, because if we do that calculation, v average equals 0 plus 0, because the graph is back at 0 at 8 seconds, over 2, which is just 0 meters a second. But that doesn't make any sense, because we can see that this graph has a positive area above the axis. Here, I can shade in. And that indicates, remember, that area is equal to the displacement. Or another way of writing that is change in position equals x final position, minus x naught, initial position. So that area that we could calculate there would be equal to what we'd get if we calculated the displacement. Since there's a positive area, the object would have moved, and 0 meters a second does not make sense. Why does that not work? Because this method works when there's a constant acceleration. and it has to be a single constant acceleration. In this case, there's a positive acceleration here. The slope of the VT graph is the acceleration. And then there's a negative acceleration there where there's a negative slope. So down here does not work. Because the acceleration changed. Okay, I'll pause and I'll talk to you about a couple more things about displacement. Okay, so let's come back to this idea that displacement is the area under the curve. So if I look at this graph, a single block on the graph would indicate a velocity of 2 meters a second, area of one block is equal to 2 meters a second times 1 second. The units divide out, they act just like variables, and we get 2 meters for each block. So then, if I look at the two sections of this graph, there are 4 blocks, so I can just see that delta x, displacement, equals the area, and that's 8 meters. And notice that the velocity is not changing, so that's constant velocity. Then, if I look at the triangular portion, well, I've got a 2 block. This is half a block, and this is half a block. So for the constant acceleration portion, then the area, the displacement, must equal 2 plus 1 meters, or 4 meters. And this makes sense. That the displacement is less than before because there's only one instant where the object during the constant acceleration phase is moving at 4 meters a second. At every other instant, it's moving at less than 4 meters a second. As time passes, the graph shows the velocity decreasing. And another thing to notice here is that this line slopes down, so this is actually a negative acceleration, but this is a positive displacement. So the two are not necessarily related to each other. You can have a negative acceleration with a positive displacement, and you can have a positive acceleration with a negative displacement. Okay, let's clear that off, and let's look at one more thing. Now, if we look at this graph and interpret the area to find the displacement, then for this graph, each block is worth 5 times 2, or 10 meters. One block equals 10 meters. So we can actually interpret where this object ends up just by looking at the graph. This is going to be half of 10 meters, 5 meters, 10, 10, 5, 5, and 5. So that would be 10 plus 10 is 20, plus 10 is plus 20 is 40. So from t equals 0 seconds to t equals 8 seconds, delta x equals 40 meters. Does this object get back to the starting point? It does. No, it does not, because let's look at the next portion of the graph. There's a negative portion here where that block would be 5, or pardon me, I forgot my numbers. That would be 10. That block would be 10 plus 5 plus 5. So it only goes 20. Now, where will it get back to its starting position? Well, we'd have to extend this graph down until we found where the area equaled 40 meters. It certainly would not be another 4 seconds at 16 seconds, because that area is going to be much larger, since we'd have a rectangle here. You imagine me extending the graph. You didn't go quite enough over, I guess. We have a rectangle here and a triangle of area. So it's going to be less than 4 more seconds. I'll leave it to you to figure out how far the object has to move to get back to the origin. But it would happen when this positive area of 40 meters is added to the negative area there, which would be negative 20 meters, plus some additional negative displacement as we continue to go farther. So that's from t equals 8 seconds to t equals 12 seconds. So I'm posing that question for you. When does the object return to x initial? Thanks for watching. Remember, what one fool can learn, another can.